Hello, class. So this is the third video on section 5.2, and when we're dealing with net area. Right? So as we saw in the previous video, what's net area? Well, it's just the area bounded by a function on some interval with the condition that if the region is above the x-axis, you make it positive. If the region is below the x-axis, you subtract it or make it negative. And of course, we saw an example of that in the first video. Right? We saw that the algorithm to approximating the net area was the same. You still just use either a left Riemann sum, midpoint Riemann sum, or a right Riemann sum. Right? And you just do the same thing. Find the change in x, multiply that by the function value at what x value. We'll just add change in x a bunch of times. Right? So the algorithm is the same. The only thing is that when the rectangle is below the x-axis, we have this negative sign show up. Now, we also saw in the previous video that in order to find net area, because net area is not an approximation, right? We want the actual area. So that in order to do that, we need infinitely many subintervals. Why? Because as we saw in previous videos, the more subintervals you use, the more accurate the approximation is. So what did we do? We defined net area as the limit as n approaches infinity of this sum here. So what was this sum? This was just a sum approximating the area with n subintervals. Right? So we went over that. So if we want infinitely many subintervals, just take the limit as n approaches infinity of that. Right? Because that is going to give you infinitely many subintervals. And as I said, theoretically, this makes sense. In practice, how do we do this? We saw there were two problems. Well, first of all, it's a limit. Is it going to exist? And then how do we compute it? We saw there was an answer for the limit question. As long as the function f is continuous, the net area defined as this limit is always going to exist. And then the last thing we did was we introduced this notation. Instead of always writing the limit as n approaches infinity of the sum of k equals 1 to n of f of x of k changing x, we just use this notation here. We just take the definite integral of f of x dx, right? And we differed this with the indefinite integral. And the difference was well, a couple differences. With the definite integral, we put the endpoints of the interval here, and it means net area. Right? For the indefinite integral, we don't put any endpoints on the integral sign, and it means antiderivatives. And as I mentioned in the previous video, of course, since we're using the same notation or almost the same, there has to be some relationship. We're not there yet, but we're going to be there eventually. So for our purposes right now, this net area, we're going to represent it as the definite integral from a to b, and that's how you want to read it, definite integral from a to b, reading left to right, of f of x dx. Again, definite integral from a to b of f of x dx. Now let's go ahead and see an example. So suppose f is integrable on the interval -2 to 2. Write the following Riemann sum as a definite integral. Okay. So what do we have here? Well, this looks like, this part here looks like an approximation of area using n subintervals. And we basically just have to go back to what this meant. Right, so look at that slide for a moment. And what do we have? So remembering that this is an approximation of net area, at least this part in red, this thing is our function. This is our function where we're plugging in the x values. So let's call it f of x of k. This part here, this is the change in x, so the length of the rectangle. This meant that we have n subintervals. And of course, it's net area because we're taking the limit as n approaches infinity. Right, so that means we're taking infinitely many subintervals. So this is net area. So again, how do we rewrite this using the integral notation? Well, how do we write it as a definite integral? Well, this is the same as, write the integral symbol. It's a definite integral. So remember, part of the information was here. You put the endpoints on the integral. The left endpoint always on the bottom of the interval. The right endpoint always on the top. this part takes care of this whole limit and sigma sum part. Then we need the function. Well, the function here, what is it? Well, we have 4 minus x sub k squared. Writing it just without the x sub k's, the function is 4 minus x squared. And then just the last thing, the change in x becomes the x. And it's as simple as that, right? Right, the limit and the sigma sum part always becomes the integral. Just remember to add the left endpoint and the right endpoint on the bottom and the top. Then write down the function, which you can always read off, right? 4 minus x sub k squared. Okay, just get rid of the k basically. And the function is 4 minus x squared. And the change in x, just change it to dx. And it's as simple as that. Now, in the next videos, we're going to try to actually start to compute this thing. It's not going to be easy. And I promise you, when we get to section 5.4, we'll find a very easy way to do this. Right? We won't have to compute any limits. We won't have to compute any sums. It'll be very straightforward. For now, we still have to use the sums, right? Because we haven't gotten to section 5.4. But we'll get there. So even though this is very theoretical, please just bear with me. We're soon going to get to a section where we can basically not forget about this, but kind of forget about it, kind of not use it again, but know where it comes from.